Hello again. In the previous lecture, we started to talk about hypothesis testing, which is, as we mentioned, as it is one of the biggest and main problems in statistics. It's the main topic in statistics, actually. And we started to talk about the philosophy behind this topic or subject. We started to talk about actually the population mean or conducting some statistical tests around the population mean. We will study some other parameters, but we start with the population mean. Actually, we looked at the steps of testing hypotheses, especially around the mean, and we talked about three main steps. The first step was set up the null and alternative hypothesis. So we start any testing hypothesis problem with setting up the null and alternative hypothesis. That's the first step in this issue. The second step is to determine the test statistic and its sampling distribution. We talk about how to decide around the test statistics, which is useful for testing such hypotheses. We said that each pair of hypotheses, null and alternative hypotheses, they have a case in which they have, for which we have a specific test statistic. So when we decide upon the null and alternative hypothesis, we should know what is the test statistic which can be used for these pair of hypotheses. So we determine the test statistic, and the test statistic is not useful without knowing its sampling distribution. So these come together, test statistic and its sampling distribution. And we mentioned, for example, Z has a standard normal distribution. That's its sampling distribution, and so on. The third step was to specify the significance level. And this is given in most the testing hypothesis questions. In all hypothesis problems, if you do not decide, it is given usually. We do not decide them themselves, but in practice, we decide about them. But usually for the exercises, we give you the significance level, but we should know how to use it. This session, in this session, we will start to talk about define, which is the fourth step, define this decision rule. As we knew the significance level and the test statistic, we should be able to define the decision rule. When to reject the test statistic, the null hypothesis, or not reject the null hypothesis. And when we talked about the philosophy of testing hypothesis, we mentioned that we usually either reject the null hypothesis and we have a good evidence against it, and it is we say the test is significant in this case because we have good evidence against the null hypothesis. Or if we do not have evidence, then we say that we do not have enough evidence to reject the null hypothesis. So it's not good to say we accept the null hypothesis, but we say we do not have enough evidence to reject the null hypothesis, or we cannot reject the null hypothesis according to the evidence which we have. That's best to say. Either we say that there is no enough evidence to reject the null hypothesis, or the null hypothesis is not rejectable according to the evidence that we have. Right, and we say this question is similar to the courtroom. In the court, if we have accused person, if the prosecutor find an evidence against that person or the accused one, then he is guilty, and he will be sentenced some years or whatever. He's be sentenced as guilty person. But if the prosecutor do not find evidence against him, so he will not be sentenced. He might be guilty, but no evidence against him. So, but still we treat him as unguilty. That he is innocent in this case. He is not. He might not be innocent, but he must be treated as innocent just because there is no evidence against. We cannot prove that he is guilty, or the prosecutor did not have enough evidence to prosecute him as guilty. Right? And this is the same. In testing hypothesis questions, the same. If we have enough evidence, then we can strongly reject the null hypothesis, and it is good evidence. But if we do not have evidence, then we do not reject him. That's the fourth step, define the decision rule. The fifth step, take a sample and calculate the value of the test statistic. And we have now a rule, decision rule, which law or formula. And then we have the sample evidence, and we substitute the figures from the sample in the decision rule, and we have an observed statistic in this case. And the last step, to use this evidence and make a statistical decision whether to reject or not reject the null hypothesis, and then we draw the final conclusion against that. So we talked about the first three steps, and now we are going to talk the last three steps and have examples. Now, the fourth step is to define the decision rule. Right? This is to define the decision rule. The decision rule is to have a test statistic or a function of the data. Using it will enable us to either reject the null hypothesis or not reject the null hypothesis. According to what? If we have test statistic and have its sampling distribution, so then we have the area under the sampling distributions curve, under the curve. Then this is the all possible values that the test statistic can take. We have the sampling distribution, then we know all possible values. For example, from minus infinity to infinity, or from 0 to 1, or from 0 to infinity. These are all possible values that the test statistic itself can take, which we find from the sampling distribution, right? And then we want from that to find the rejection region. What possible values that the statistics itself, the statistics itself can take, for which we can reject the null hypothesis, and what are the possible values for the test statistics that for which we must reject the not reject the null hypothesis, right? So the rejection region is a subset of the possible values that are extremely unlikely if H naught is true. For which H naught is true, it's simple, nearly impossible that the H naught is true. The statistic is, or the hypothesis, null hypothesis is true, and thus this will lead us to reject H naught. The non-rejection region is the same, the remaining values, and in fact bigger usually, more values here in this region, more values here in the rejection region, very small values, but the non-rejection region are the bigger region, which means that there are much more values than that the rejection region can take. Um, the remaining part of the possible values. So we define the values or the region that in which the test statistic can take and divide it into two parts. One we call rejection region and the other we call the non-rejection region, and separated by values from this value to this or from this to this. These values are called critical values. Critical values. The critical values separate the rejection region from the non-rejection region, right? For example, if the X bar is normally distributed and sigma is known, then for the null hypothesis, it is H naught, mu equals mu naught. Then we can alpha, the significance level, that's the other step. Alpha is a small value, and it is quite likely that it is a statistic between minus z half alpha and plus z half alpha. If it is less than minus z alpha or greater than z half plus z half alpha, then we reject the null hypothesis because these are the rejection region. But if the test statistics fall between minus z alpha and plus z half alpha, if the test statistics fall between minus z half alpha and plus z half alpha, then this is non-rejection region. So we cannot reject the null hypothesis. But on the other sides, the extreme values, small or large, these are the rejection region. And if the test statistics fall between these parts, in the extreme parts, then we reject the null hypothesis. For this, we call it the rejection region. If the value of the test statistic calculated from the sample at hand happens to be below minus z half alpha and or above z half alpha, we are willing to reject the H naught, the null hypothesis, like that here. This is minus, this value is a critical value. It is minus z half alpha. And this another critical value, the plus z half alpha. This, from this to this, it is non-rejection region or acceptance region, sometimes we call it acceptance region, but it is better to say non-rejection region. And this value is the critical region here. This is the rejection region, and this one is the rejection region. So these region are the rejection region are the extreme value, right? And this region, this area is 1 minus alpha. So this area is half alpha and this area half alpha. So we can get the minus z half alpha and the plus z half alpha from the standard normal distribution table, from the table or from Excel itself. It gives you these values. For example, if 1 minus alpha equals 95%, is confidence level, then the significance level alpha is 5%, 1 minus 95%. So the 5% divided into half alpha equals 1.0225. And then from the table we get this value z half alpha, and here it will be minus z half alpha, and here z half alpha. Z half alpha from the table we can get it as 1.96. 1.96. So this value will be minus 1.96, and this value will be plus 1.96 if alpha equals 5%. And these values are obtained from the standard normal distribution table, right? And this is non-rejection region, and these values, small values here, are the rejection region. Z half alpha and minus Z half alpha are called critical values. Example, at the 5% significance level, Z half alpha, which means in that example, Z half alpha equals 1.96 from the normal distribution table, standard normal actually. So the decision rule will be reject each node value of the test statistics calculated from the sample, which we call it observed test statistic or observed Z. Observed Z is either smaller than, if the observed Z either smaller than plus minus 1.96 or bigger than plus 1.96, right? The fifth step is take a sample and calculate the value of the test statistic. Take a sample and calculate the value of the test statistics. So from the figures in the value, we must calculate first the estimate the parameter itself. If it is mu, estimate mu by x bar. We calculate x bar, and then we calculate the sigma, or if it is not known, we calculate the we estimate sigma x bar. We use S x bar, the standard error of x bar, and usually these are given. So, and substitute them into the formula. We substitute these values, we substitute into the formula of Z, actually. We substitute them into Z. So the sample values that are used to calculate the Z obs or Z observed Z. So for example, if given n equals 200, x bar equals 435, and sigma, that sigma, standard deviation of the population here, is 84, then we know as n is large and the standard deviation of the population is known, then the test statistic Z is Z. So we calculate Z obs by first, we have x bar equals 435, and we have sigma equal 84. Then we calculate the standard error of x bar, which is sigma over square root of n, which is 84 over square root of 200, and this goes to 5.94. Using that as the standard error of x bar, we can calculate the observed Z, which is x bar minus mu naught over the standard error of x bar. Mu naught, by the way, is here 420. So the x bar 435 minus 420 over the standard error of this one, which is 5.94, and that goes to 2.525. That's the Z obs or observed values. This is the observed Z value. So we remain the last step. We have now the observed test statistics and critical region, and we have the observed Z value, so we can make a statistical decision whether to accept or reject the null hypothesis. Reject or not reject, actually, the null hypothesis. So we make statistical decision by either decide whether or not to reject the null hypothesis, answer the original equation. That's the conclusion. So if we decide to reject or not reject the H note, we can draw the conclusion. Actually, that's the last step. For example, we have the Z observe Z equals 2.525, which is greater than 1.96, which that is half alpha, and that's much greater than the tabulated Z from the table. Then we reject H note. It is much bigger, so it falls in the rejection region. So we reject H note and conclude that at the 5% significance level, that this year's average of HC score is different from 420. So the null hypothesis was mu equals 420, and the alternative hypothesis was mu not equal the 420, and the test we concluded that the test is in favor of the alternative hypothesis, not the null hypothesis. So we conclude that the average is different from 420. It's not equal 420, right? Another things which we usually call is, which we mentioned sometimes in testing hypothesis, is one-tail and two-tail test. One-tail and two-tail test. So if that's easy, actually, if the null hypothesis is mu different from mu naught, that's if the alternative hypothesis, sorry, if the alternative hypothesis is mu not equal mu naught, that means we reject the null hypothesis if mu is less than mu naught, or if mu is greater than mu naught, in both cases. So again, if H naught is mu equals mu naught, and the alternative hypothesis is mu is not equal mu naught, then we reject the null hypothesis if mu is greater than mu naught, or if mu is less than mu naught. Then in both sides we reject the null hypothesis. Then we have rejection region in both sides, right and left, in both sides. So we call this test in this case one-tail, we call it in this case two-tail test. Two-tail test, because we reject the null hypothesis in both cases. Or sometimes we call them two-sided test. Two-tail or two-sided test, because we have rejection region on both sides. If it is less than mu naught or greater than mu naught. However, if we reject the null hypothesis only if mu is less than mu naught, so in that case the alternative will be mu is less than mu naught. That's the alternative. Or in one case, that's the only case. Or if the only case we reject mu naught if mu is greater than, only if it is greater than mu naught, that's only one side only. So in these two cases, we call the test as one-sided test or one-tail test. Both the same, one-sided test or one-tail test, right? One-tail test. So it's the same. So the alternative hypothesis will compel us to call this test either one-tailed test or one-sided test, or two-sided test or two-tailed test. In two-tailed tests, usually we have each node mu equals mu naught, and that's important. And each a alternative hypothesis mu is not equal mu naught. So the rejection region both sides and alpha will be divided into two areas, half alpha on the left and half alpha on the right. But if the alternative hypothesis the alternative hypothesis is mu less than mu naught. In all cases, the null hypothesis is mu equals mu naught in all cases. But the alternative can be mu not equal, or mu less than, or mu greater than. This one, or both these cases, we call it two-sided test or two-tailed test. In this case, we call it left-tail test or left side test, left tail test, because mu less than mu naught. So the rejection region in the left, the small area, the small parts, small values, I mean, small values, mu less than mu naught. And in the other case, if mu is greater than mu naught, we call it right tail test, because the rejection region on the right. All the rejection region will be in the right. So all alpha will be either on the left in first case, in this case, or all alpha will be on the right. Right? So assuming again that the test statistic Z, the decision mechanism of the left tail and right tail test can be illustrated in the following. So that's the left tail here. Left tail here, rejection region in this case, and this value, all this value is alpha. And from this point up to end, up to infinity here, all is 1 minus alpha. Only this area is alpha. So we get minus z alpha, not z half alpha, z alpha, because it is one tail or left tail test. It's not two tail test. So alpha here, all alpha here, not half alpha. And this can be found from the table, the normal distribution table, with all this value is alpha, right? We do not divide alpha in this case. And also in the other case, for the right tail test, and the opposite. So this is non-rejection region, and this is the rejection region only on the right, all with all this value alpha. We said in the two-tailed, we have the rejection region or critical regions on both sides, and each side will be half alpha. But for one tail test, all the rejection region is alpha all the time, right? Then that's important to understand, and we can take an example about that. The example says the average monthly wage of all workers in a large factory is $626.4. In a random sample of 100 male workers in the factory, it was found that X bar equals $682. X bar equals $682. Assuming that the standard deviation is $82.09, can we conclude that with alpha equals the significance level, alpha equals 0.055%, that the mean monthly wage of male workers is greater than the overall mean monthly wage, right? This is the example, and we say this is mu, all the $626.4 mu, because it is the average monthly wage of all workers, population mean. This is the population mean mu, and the X bar is what is 682 to the X bar, and n equals 100, right? Then the first step, we will follow the 6 steps which we described earlier. Now we follow all the 6 steps from the beginning. The first step is the question suggests that always we have H naught mu equals mu naught, which is what? 140. But the question was that mu is greater than or not. So the alternative hypothesis is mu is greater than 626.4, right? And this is from the actually the question itself. We can write down the null and alternative hypothesis. The null have always the equal sign, always. But the alternative can be not equal or greater than or less than one of the three. But in our question, we want to decide if mu is greater than, we'll have an evidence that mu is greater than 626, right? From this figures which we have in the sample, right? The second step is to decide the statistic. As we have in 100, very good, very big, is bigger than 30, and also sigma is known. Sigma is given, known. Then the test statistic definitely is Z in this case. In this case, test statistic is Z. So no problem. We have the test statistic, and the significance level is given also, which is 5%, 0.05. Alpha is the given. So we can find the critical region or the critical values. That first we have, as here the alternative hypothesis has this sign greater than, then we have one-sided test. It is actually right tail test. Right tail test. And alpha we do not divide it into two parts. So we have to decide the critical values from one-sided test. As one-sided test, we have to compute or find from the standard normal distribution table Z alpha, not Z half alpha, which is Z 0.05, and from the table we get it, which is equal 1.645, right? Then we have this is very much less. We have the note value of the statistic from the sample is greater than that. We will reject the H naught. We will reject H naught if, according to that, if the statistic observed statistic is greater than that. What is the observed statistic then? We must calculate. Before calculating the observed statistic, we calculate the standard error of X bar, which is sigma over the square root of n, which comes to 8.209. That's the standard error of X bar. Then we can compute the observed Z bar minus mu naught over sigma X bar, the standard error of X bar, and we have X bar equals 682 minus 626.4 over 8, this value 8.209, and the result will be 6.77, which is definitely much greater than the tabulated Z, which is 1.645. So we can decide whether to reject or not to reject, and actually, in fact, as the Z observed Z equals 6.77, which is much greater than 1.645, the tabulated Z with the alpha on one side, then we must reject the H note and conclude that at 5% level of significance that the mean weekly average of male workers is greater than the overall mean monthly wage. This is the last step, right? The population standard, if the other case, in all cases we discussed at the beginning, the case where either sigma is known or the sample is big. But if the sample is small and the population standard deviation is not known, we were talking about if the population standard deviation is known or the sample is big. We use the statistic as Z. But if it happens that the sample is small and the population standard deviation is not known, then sigma is unknown and we have to estimate it. Estimate Z, estimate sigma with the sample standard deviation. We substitute S instead of sigma. But in that case, the standard error of X bar is replaced by its estimate. Estimate the standard error. So in this case, we have the same formula of this statistic, but the sampling distribution will change. It will be, instead of Z, it will be T, student T distribution. We talked about this in the previous chapter. So in this chapter, we know what is this, the student T test and how to use that T table, T distribution table. So we use the T student T table, not the Z table, not the standard normal table in this case. That's the difference. And all other steps will be the same. So only this difference. If the population standard deviation is not known and the sample is small, then we cannot use Z because we will substitute instead of sigma, we use S instead. So as we change S sigma to S, then we must use the student T distribution table instead of Z table, standard normal table. So that's the difference. We estimate sigma and use T instead of Z, right? We use T table instead of sigma. And everything will be the same. All the steps will be the same. We must follow the 6 steps as we mentioned earlier, right? Have another example. This example, a survey of 20 household families here reveals that the mean and standard deviation of annual expenditure on clothes are $387 and 60 respectively. That means the mu is 300. No, not mu, it is X bar because the survey of 20 households from that 20 household, X bar is 387 and 60 respectively. Can we conclude that at the 5% significance level that the population mean annual expenditure is less than $400? Can we conclude again? Can we conclude at the 5% significance level that the population mean annual expenditure is less than $400, that means if mu is less than 400, given that n equals 20 and s equals 60 and x bar equals 385 equals 60 and n equals 20. Can we conclude that mu is less than 400? Then we can follow the 6 steps. We have here mu naught equals 400. And here, in this case, the null hypothesis is mu equals 400. We said that always the h naught or the null hypothesis, the sign here is equal. But we must put here inequality. The question was, or the problem wants us to examine whether mu is less than 400. Do we have from the sample an evidence that mu is less than 400? So this is the alternative hypothesis, because we want to find an evidence against the null hypothesis, which means that this is true, right? So we have n equals 20, which is small, less than 30. That's a small sample. And sigma is not known. We know it's not sigma. S is given. So we are in the second case. Small sample and unknown sigma. We have S instead. So we cannot use Z. We use T distribution. And in this case, we use the T distribution, and we have the third step, alpha equals 5% or 0.05, and we have as here the the alternative hypothesis, the sign here is less than, which means that the rejection region on one side we have a left tail test, and then we do not divide the alpha, we keep it as it is alpha, and we compute from the table from the t table with n minus 1 degrees of freedom, which is 19, the t alpha, which is t 0.05, and we find it in this case the minus 1.729. 1.729, and as long as it is in the left side, it will have the minus sign, because all the left hand side has a minus sign, because the t distribution is symmetric around 0. So all the values on the left are minus, and all values on the right are plus, positive. Negative on the left and positive on the right. So this t from this distribution become 1.729, and we give it the minus sign, right? So we decide to reject H naught if the value of the test statistic calculated from the sample is smaller than this value, critical value, right? So we calculate the value. First, we calculate the standard error of x bar, which is s over square root of n, which is 60 over square root of 20, which becomes 13.42. And then the observed t will be x bar minus mu naught over standard error is x bar, and the result will be the 387 minus 400 over 13.42, and the result is minus 0.969, which is very small and less than the critical values, less than the critical values. So we can conclude that this is not in the rejection region because it's not much less than, it's not less than, it's greater than the critical value because there is a minus sign here, minus sign, so it is greater than, it falls on the right hand side of the critical value. So it will not fall in the rejection region. It will fall actually in the non-rejection region. So in this case, we fail to reject. We cannot reject each node because it's not in the rejection region. It's in the non-rejection region. So at 5% significance level, there is not enough evidence to conclude that the mean expenditure is below $400. So we do not have enough evidence to conclude that the mean expenditure is below $400, and that's it for this subject, which is testing hypothesis around the mean. In the next session, we will talk about testing hypothesis around the population proportion. We finished by now the testing hypothesis problem around the population mean, and see you next session. Bye bye.